students. Today we discuss about the one of the part of photoelectric effect, which is known as Einstein Photoelectric effect. That means for which Einstein get Nobel Prize. Okay, for which Einstein gets Nobel Prize. That is Einstein Photoelectric effect. Already we know what is photoelectric effect. Already previous classes we have to discuss about photoelectric effect, which is that means when light energy is incident on the metallic surface, then the electrons are ejected from it. That means we get current energy, that means electrical energy, by using light energy. So that is the phenomenon of photoelectric effect. Okay, so today we discuss about the Einstein photoelectric equations. So how Einstein explained his famous experiment of photoelectric effect, which is known as Einstein photoelectric effect. Okay, so according to Einstein, E equal to mc square. That means mass of a particle is equivalent to energy. That means E equal to mc square. Okay, Einstein explained his photoelectric phenomena on the basis of Planck's quantum theory. Okay, Einstein explained his photoelectric phenomena on the basis of Planck's quantum theory. Okay, so according to Max Planck, light radiates in discontinuous bundle of packets, and these packets are known as quanta. Planck's mate light kini kisman continuous bundle of packets of emit koribo pare, and these packets are known as quanta, and each quanta has a energy that is h nu. Each quanta have a energy that is h nu. Okay, so this if h nu amount of energy, that means energy of the ultraviolet radiation, that is h nu. If h nu amount of energy is incident on this metallic surface, that is cathode, in the gas discharge tube, evacuated glass tube, the gas discharge tube, there is a cathode and there is a anode, which has two electrodes known as cathode and anode. That dual electrode thake, edalok ki boli koa hoy gas discharge tube to, edalok koa hoy cathode aru edalok ki boli koa hoy anode. Okay, when light energy is incident on the metallic surface, then electrons of the metallic surface absorb this energy, that means light energy, for which these electrons becomes excited. Okay, then after excitations they are released from the outermost shell of the metallic surface, for which they are liberated or ejected from it. Okay, so the amount of energy which is required to eject the electron from this metallic surface is known as work functions. That means this minimum energy is used to liberate the electron from the metallic surface is known as work function. Okay, and remaining energy which is used as maximum kinetic energy to move the electron from cathode to anode. Okay, so Einstein explained this phenomena on this Planck's quantum theory. Okay, so how Einstein explained his equations? First you see, if h nu energy is incident on metallic surface, then how it is converted into work function and kinetic energy. Okay, see. So here you see, so this is Einstein, this energy h nu. If h nu amount of energy is incident on this metallic surface, then minimum energy, which is known as W naught. W naught means this is work function. So W naught energy is used, minimum energy is used to liberate the electron from the metallic surface, and remaining energy, that is half of m Vmax square, okay, that is maximum kinetic energy, is used as kinetic energy to move the electron from cathode to anode. Okay, so this h nu, according to this conservation of energy, this h nu is divided like this: h nu equal to W naught plus half of m Vmax square. Okay, so here you see half, that means maximum kinetic energy equal to h nu minus W naught. So W naught is the work function. So we know. So work functions, this minimum energy. So we know under what conditions the electrons are ejected from the metallic surface. That means if a minimum amount of energy frequency or suitable frequency is incident on the metallic surface, then the metallic surface eject the electrons. So that frequency is known as threshold frequency. Okay, so what is threshold frequency? The minimum frequency required, minimum frequency incident on the metallic surface required to eject the electron from metallic surface is known as threshold frequency. The minimum frequency required incident on the metallic surface to eject the electron from it is known as threshold frequency. Okay, so if nu naught here, nu naught be the threshold frequency, then work function this W naught equal to H nu naught. This W naught equal to H nu naught. Okay, so here we get this W naught equal to H nu naught, then this half of m v max square equal to H nu minus H nu naught. This half of m v max square equal to H nu minus H nu naught. Okay, so this is known as Einstein photoelectric equation. So this is also Einstein photoelectric equation, and this is in terms of work function, and this is in terms of threshold frequency. Okay, so this is the Einstein photoelectric equation. Okay, so this kinetic energy, this is Einstein photoelectric equation. Okay, this is Einstein photoelectric equation. So we know this previous class we discussed about the stopping potential. So what is stopping potential? Stopping potential is the negative potential, negative anode potential at which the photocurrent becomes zero. That is stopping potential. Okay, so see this stopping potential means the negative anode potential for which the photocurrent becomes zero. That potential is known as stopping potential. We know. So what happened in stopping potential? In stopping potential, the photoelectron becomes zero. So in that case, the amount of work done due to stopping potential is equal to the maximum kinetic energy of the photoelectron. In that case, what happened? The work done due to stopping potential becomes equal to the maximum kinetic energy of the photoelectron. That means this maximum kinetic energy is equal to this K maximum kinetic energy maximum equal to half of m v maximum square equal to E v naught. E v naught. Here E means electron, photoelectron, and v naught means stopping potential. If you see, this is kinetic energy is equal to E v naught. Okay, so E v naught, how it is get? We know W equal to QV. V means electric potential, W means work done, then W equal to Q into V. Okay, so Q means Q is the charge, here Q is the electron. So here we get W equal to E V. Okay, so from this we get this formula, kinetic energy equal to half of m v max square equal to E v naught. Okay, so now we discuss how stopping potential is related with threshold frequency, work functions, and okay. So first let's see how it is related with, how stopping potential relate with threshold frequency and work function. Okay. So here you see, now we discuss about determination of Planck's constant and work function from Einstein photoelectric equations. Okay. So how Planck's constant, that means Planck's constant is H and work function is W naught. How it is determined? By using Einstein photoelectric equation. Okay. So we know V naught with the stopping potential. Okay. Stopping potential If V naught be the stopping potential, then we already know this kinetic energy maximum equal to E V naught. Okay, so we know the Einstein photoelectric equation, kinetic energy maximum equal to H2 minus W naught. So this is equation number 1. So that's Einstein photoelectric equation. Then equation this becomes this E V naught equal to H2 minus W naught. Okay, so this E V naught equal to H2 minus W naught. Okay, this V naught equal to H by E nu minus W naught by E. This is the most important relation between stopping potential and work function. This is the most important relations. It's one of the most important equations in between stopping potential and work functions. Okay. So already we know in the experimental study of photoelectric effect, already we know that means stopping potential is varied due to change in frequency of incident radiations having frequency more than threshold frequency incident on the metallic surface for constant intensity of light radiations. We know, okay? I already paisho that how stopping potential in the experimental study previous class already I discuss korisu. Already previous class we have to discuss. So how stopping potential is changed by changing frequency of incident radiations at constant intensity of light. Okay, we know. So if the frequency is increased, then stopping potential is increased. Here you see. Already this equation saying, this equation explain this. This is already constant in that metallic surface. This W naught is constant. E is constant. That means this value is constant. We know. So if nu is increased, that means nu. If nu is increased, then stopping potential is increased. That means if the frequency of the incident radiation is increased, then stopping potential of this surface of that metal is increased. This is experimentally proved. If you face some example, if you face some question, so how you explain that the stopping potential is increased due to increasing frequency of the incident radiations falling on it. So this is the main mathematical explanation. It is a mathematical explanation how you prove the stopping potential is increased in a metallic surface due to increasing frequency. Okay? So from this, if you draw a graph, like experimental study, suppose the graph is stopping potential frequency curve. The name of the graph is stopping potential today. If you consider stopping potential along y-axis and frequency along x-axis, then we get a graph. Suppose this is y. Suppose this part is y, and this part is m, and this is x, and this is c. Okay? That means this equation represents the equation of straight line. Then what will be the shape of graph? Stopping potential and frequency. This is a straight line. This is a straight line. From this, if you consider stopping potential along y-axis, then frequency along x-axis, then the graph will be like this, straight line. Y equal to mx plus c. This equation satisfy what? Equation of straight line. Okay. So here v naught, this v naught is y, m is h by e, nu means x, and c means w naught by e, minus w naught by e. This c is negative, c is intercept on y-axis. Okay. So here c is negative. Okay. And we get a graph like this. We get a graph like this. This is frequency. Suppose this is nu and this is w naught by e. This is w naught by e. Here, this is slope. This is negative slope. Oh, sorry, positive slope. That is h by e. This is slope theta. Okay? So from this, we get this m equal to h by e, that is slope, and c equal to w naught by e, y intercept. Y-intercept. Okay, so from this m equal to h by e, or c equal to w naught by e, we get the value of Planck's constant h and the work functions w naught. Okay, so here you see that from this graph, suppose m equal to h by e, h means Planck's constant, and is equal to, this is slope means tan theta. That means h equal to e and slope of potential frequency curve. E into slope of potential frequency curve. That is stopping potential. Okay? Stopping potential and frequency curve. This is the Planck's constant. Next, so how you get C, that is work function. This work function W naught equal to E into Y intercept of V naught and frequency curve. This is so how you determine Planck's constant and work function from potential frequency curve. Okay, so what is Planck's constant? H is how you determine Planck's constant. This H is equal to E into slope of potential frequency curve. That is tan theta. H equal to E tan theta. Okay, tan theta means slope, and W naught equal to E into Y intercept. Okay, that means is M equal to H equal to E tan theta, or E M, or M means slope, and W naught equal to C into E. C means Y intercept and E means electronic charge, where E equal to 1.6 into 10 to the power minus 19 coulomb. Okay, so from these two equations we can determine the value of Planck's constant and work functions. From these two equations we determine the value of what? Value of Planck's constant h and work functions w naught. Okay, so next we discuss how stopping potential is related with threshold frequency and threshold wavelength. Okay, how stopping potential related with threshold frequency and threshold wavelength. Okay, see. So now you get relation between stopping potential and threshold frequency. So already we know this equation of straight line y equal to mx plus c is v naught equal to h by e nu minus w naught by e. Okay, already we know. So this v naught equal to h by nu minus this work function w naught equal to h nu naught, already we know. This w naught equal to, already Einstein equation we know, w naught equal to h nu naught. Okay, so putting this value h nu naught, we get this. This v naught equal to h by e into nu minus nu naught. Already h by e common, then we get nu minus nu naught. So this is the relation between stopping potential and threshold frequency. This is the most important relation between stopping potential and threshold frequency. Okay, so next we know there is a relation between speed and frequency and wavelength. Speed, frequency and wavelength. Okay, so we know in already wave or ray optics, already we know the speed of light is c equal to nu lambda. Okay, this c equal to nu equal to c by lambda. C means speed of light in vacuum. Okay, so this nu equal to c by lambda. This nu naught is a threshold frequency, is equal to c by lambda naught. This lambda naught be the threshold wavelength. Okay, is c by lambda naught. So is a lambda naught threshold wavelength. Then substitute this value. We are able to substitute value. Then we get v naught equal to h by e into nu means nu value to c by lambda minus nu naught value input value c by lambda naught. Then h by e into c, it will be common. Then h c by e is common. Then we get 1 by lambda minus 1 by lambda naught. So this is the relation between threshold wavelength and stopping potential. This is the relation between threshold wavelength and stopping potential. Okay, so this is threshold wavelength, and this is the relation between stopping potential and threshold frequency, and this is stopping potential and threshold wavelength. Okay, so this is the different relations of the quantities relates with Einstein photoelectric equations. Okay, so next class we discuss about most interesting part, which is known as de Broglie's hypothesis. That means we discuss about matter wave. Okay.